Hi guys, I'm Zach McGill, and this is Lab 4 for Physics 2211, the physics of extreme sports with ropes. So today we're going to examine the motion of a spring and mass system in which the mass swings in an up and down motion while bobbing on a spring. We'll take the data collected and put it in a CSV file, which we can then import into a VPython code. We'll run the code and compare the predicted motion to the actual motion. Then we'll discuss the energy principle in relation to this problem, and look at two big ideas, the energy principle and the momentum principle. So first we're actually going to look at the video and tracker really quickly. I started recording about 10 frames into the given video because that appeared to be the start of the motion. As we can go ahead and play, you can see I track the center of mass of the object as it moves up and down along the spring. Here the data is kept in tracker, and then it's plotted up here in two graphs. The first one showing the translational motion in the x direction, which is fairly minimal, and the second showing a much more substantial and fluid, more easily traceable movement in the y direction, which we expect from the smooth flowing movements of the spring we saw. I'm going to go ahead and skip just down to actually looking at the code itself instead of these screenshots. So the first thing you'll see is a setup window, which is really nothing too interesting to talk about here. Some initial conditions: we have the ball's mass at 0.402 kilograms, the ball's initial position, which was given to us in the video, a small delta t value as is usual, constants for both gravity and spring constant, and as well as the initial relaxed length of the spring. These values can be found using the method used in the example video. Used the exact same method, got the almost identical values. And continuing, we need to calculate both the length, which is just the length of the spring at one time, a unit vector for the length, as well as a variable called s, which is again the magnitude of the new length minus the at rest length. We'll be monitoring three energies throughout this video. The first is kinetic energy, which is 1/2 mv squared. The second is gravitational potential energy, which is just mgh. And the third is a spring force potential energy, which is 1/2 ks times s squared. All of these written in code here. We get to the bulk of our code, which is a while loop that continuously calculates velocity. This is done by combining the force of gravity and the spring force, the two forces acting on the system, into one FNet, using Newton's second law to update the velocity as we've done in every lab prior, and then using that new velocity to update the position again as we have before. We need to have these three values written again inside our while loop. And here we calculate just the change in both potential energies and kinetic energy, and those are the three things in combination with total change in energy that we're going to be looking at a graph when we run the code. So we're going to go ahead and run the module to see what we get. It's going to run for t equals 5.5 seconds, which obviously this is slowed down to give you a look at how things move. To note, obviously it looks like our system, we have a mass bobbing up and down, a constant force of gravity. Up here it's difficult to see, but we have a spring force acting upward. In the graph itself, we have the two potential energies seem to cancel each other out. They're symmetric across the x-axis. That's because when gravitational potential energy is at its highest in this case, when the spring is at its highest point, that means that the potential energy of the spring is at its lowest because the spring is most relaxed. The opposite can be true at the bottom position. There is some change in kinetic energy because the ball does speed up and slow down in a constant way, or not a constant way, but a repetitive way throughout the video. But most importantly, the delta E, this yellow line, is constantly 0. So getting back to our slideshow here, we can look at our first what does it mean question, which asks us if the energy principle is satisfied. The graph we just looked at shows us that the energy principle is satisfied. The change in energy of the system total is equal to 0, and that's what this yellow line tells us, is that total energy changes 0, even if parts of the total energy are constantly changing. So the second what does it mean question asks us to find oscillation periods in both the x and y components. You can see my values calculated here. They're very much similar, which makes sense because the translational motion seemed to be taking just as much time as the up and down bobbing motion. These values are very close to the values calculated in the video on a Coursera, which should be expected because we're using the same tracker video. The reason for a little discrepancy is because the tracker video was kind of difficult to analyze. There were a lot of data points and a lot of places for error, especially in the x direction, where just a very small change in click had a huge ramification on this period value. Alright guys, that's the end of my lab. Thank you for watching.